Hey everybody, this is Dr. Brooker here with just a short description of the mass on a spring simple harmonic motion lab activity. So this is Blackboard that you see. If you just go to Learning Materials, it's in the Week 13 folder. And you see down here simple harmonic motion folder. And then here's the actual activity, and you find it right here. It's a Word document. So once you complete it, there's no big lab write-up for this one. You just complete it, and either write it out by hand and scan it in somehow and get it to me, or you can just type it out right on the sheet, and then you can upload it here. So attach files, upload it that way. That's the easiest way for me to keep track of it. If everybody emails me the same thing, it comes at different days, it's hard to keep track of. So if you can upload it here to attach files, that makes it a lot easier. Now if you can't get that to work and you want to email it to me, I still will accept it that way, but just from my perspective, if you can just upload it here, that would be a lot easier. Okay, so here's what it looks like, and it's not due until April 24th, so you have 2 weeks to finish this, and this is going to be our final lab activity, so you've got 2 weeks to finish it. So let me click on it. You can see what it looks like. I'll open it up. And it's one of these FET ones, as you can see here. So to open up the FET, I'll just do Control click, or you can copy that and put it into your browser. Whoops, Control click. And there we go. It looks like this, and what we're going to be using is the one over here called Lab. I just wanted to show you a few things about this. Okay, so here's a spring. We've got some masses over here, 100 grams, and these are unknown masses. Part of the lab is to use simple harmonic motion to find these masses. We don't know what the spring constant is, so for the entire lab we want to set this on large. Move it all the way over here to large. We'll select a few of these. Displacement, natural length, and you can see the blue line comes here. Mass equilibrium, we can use that if we want to. And movable line. And the movable line you can move wherever you want to. We have a few other things over here. There's a meter stick that you can move around to wherever you want to. I can put it back over here. There's a stopwatch here, so we can use the stopwatch. We'll just be working on Earth, so we'll use Earth. There's also a damping feature. Now if there's no damping, that means there's no internal friction. The thing will oscillate forever. Let me actually show you how this works. None. I can take the 100 gram mass, attach it to the spring, let it go. It'll bounce around forever. Now some of the lab we don't want it to be moving, we want it to be stationary. So if I increase damping to a lot, then I can see that it's displaced. So let me take the mass and remove it. To remove it, you just hover over it, left clicking and moving the mass off to the left. So you can see this is the natural length of the spring, and if I put this here and let it go, because I have some damping on, now it's been displaced, and it's moved this much from here down to here. So right now I know the spring force is up, mg is down. I can calculate the spring constant if I wanted to that way, right? Mg down, kx up. I could calculate the spring constant if I wanted to. Okay, so damping, I use that to get the thing to stop, because if there's no damping, it'll keep moving. Okay, so let me remove this again. So basically that's what you do with the first part. Take the mass, add it to the spring, like this. Because I've got damping on it, slows down. And then I can figure out how much it's moved. I can move this around to a nice convenient spot. Maybe I'll do this. So I started at 50 centimeters. Now I've displaced down to 60 centimeters. So again, I've got the spring force up. That's kx. I've got mg down. Those are equal to each other. I can calculate k. Okay. That's just for one mass. Let's do it for another mass. I'll move this up to 100. Sorry, it's already at 100. I'll move it up to 150. It'd be easier if I can slide it, but it's not letting me. Oh, there we go. Same thing, I want to know how much I've moved from equilibrium. I can go back up here to equilibrium, and you could estimate how much it's actually moved there. And this looks like it's down to about here, that sort of thing. And maybe move it up to 200, whatever it says in the handout. It's the same spring. The spring constant shouldn't change, but the more mass you put on, the more it stretches. So we can get the spring constant that way. We're going to be always doing that for large. Now the second part, we're actually going to get this thing to oscillate, and when you look at the lab handout, you'll see there's a formula for the period of a mass on a spring. So the period is equal to 2 pi times the square root of m, and m is the mass on the spring, divided by the spring constant. Well, now you know the spring constant because you've just calculated it from the first part of the lab. So now that we know the spring constant and we know the mass, we can calculate the period from that equation that I just said. Okay, so let me put this back to 100. Move this out of the way so I can see what I'm doing. I'm going to move this back down to 100. Now I still got damping on, so it's actually stopped. So I'm starting here, a nice convenient spot. Maybe it could be the top of the mass, however you want to do that. So I'll get the ruler here. This is the equilibrium position. So I'm just having it at 50 centimeters. You want to take the mass and displace it from equilibrium and let it go. We want to do this with no damping, though, because we want it to move around. So none. I'm going to take this mass, displace it about 10 centimeters from equilibrium. So that's about there, I would say. That's about at 60 centimeters. Now, if you want, you can make it a little more precise. Oops. See, it's moving because there's no damping. Let me slow it down. Okay. So I'm starting at about 50, and I'm going to displace it 10 centimeters. So I want to displace it down to 60. Let me get rid of the damping again. Put the top of this at 60. There's no damping. If I let it go, it's going to keep moving around. As you can see, it's doing there. Now we want to try to measure the period. The period is the amount of time it takes to go from one position all the way through a cycle. So from down all the way to up to back down. It's really hard to see it now, but what I'm going to click here is the slow button here. Okay, good. This will make it a lot easier. So when it gets to the top, I'm going to start the clock. Start. And the period is the amount of time it takes to go back to that spot. So about 0.56 seconds. Okay, you want to do this 3 times. So I want to stop it again. So record that. That's 0.56 seconds. That's the period of oscillation. It's a lot of damping on. Go back to normal for a minute. Have it stop. And repeat the experiment again. Whoops, it looks like it. Can't tell if it was still moving a little. Let me go back up to lots. Okay. Alright, so I'm going to displace it again. Let it go. Let me reset the clock here. And again, let's go to slow so we can actually see what's going on. Start the clock. All the way down, all the way back up. Stop. 0.55. Alright, so that's pretty good actually. And then do it one more time, get the average of those periods. Okay, great. So that's the way to measure the period. That's experimentally determining the period. You can compare that to what you got for the equation that I just detailed. So we'll measure it experimentally and compare it to what you got before. So how does the amplitude come into play? I just did it about 10 centimeters from equilibrium. Let me stop this. Now I want to displace it. Instead of 10 centimeters, I think it's 20 centimeters. So let's actually do that. Whoops, I got to get rid of the damping now. And then displace it 20 centimeters from equilibrium and let it go. And now what is the period? From looking at it, it's hard to say. It's got to move a farther distance, but also it's moving faster. How do those effects work together? So actually do that and measure the period. You might be surprised by what you get. If you look at the formula for period, you might not be surprised, though. How does the period depend on the amplitude, or does it? Hint. Okay, the final part is to measure the unknown masses here. Now the way that we can do that is the following. Let's slow this thing down. And I'll remove this mass. I think we start with the red mass. Put the red mass on. So the red mass is obviously heavier. Now we can measure the mass by measuring the period. Remember, you know the spring constant. We don't know the mass, we don't know the period, but we can measure the period. So we're going to displace it from equilibrium and actually measure the period. So this looks like it's about 72 centimeters. Let me displace it down to like 82 centimeters, something like that. Okay, so what I'm going to do is move it down to 82 and let it go. When I actually do it, I'm going to have to get rid of the damping though. Okay, so it's stopped. Get rid of the damping. Move it down about 10 centimeters. Does the amplitude even matter? You'll know that by the time you get to this point. And then I can let it go. And I can choose slow here. And pick a nice convenient spot. Looks like I'm going to wait till it comes back around again. Okay, so when it hits the very bottom spot, I'll hit go. It's going to come up, come back down, and then I'll stop the timer. 1.05 seconds. So that's the period. I know the spring constant from earlier. I'll have to use that equation, do a little bit of algebra, and figure out the mass. Probably do this 3 times and get an average amount of time though. So then when you have the average period, you know the spring constant, you can calculate the mass. And then repeat that part for the third part. Or sorry, for this unknown blue mass, I should say. Okay, play around with it. It's kind of a fun little FET. We don't really do anything with the energy graph here, but you can explore that if you want to. Mostly we're looking at mass, spring constant, period, and amplitude. Okay? Have some fun with it. And again, there's no big lab write-up. Just complete that Word document and I sent you. Fill in the experimental numbers, the calculations, and then get it back to me. And you have about 2 weeks to do that. Any questions, email me, and I'll talk to you soon. Bye-bye.